Everyone, so we're going to be getting started. Thank you all for coming. So this is our fourth, actually, workshop in the series. It's going to be on binary exploitation. And, with that, I'll pass it off to Gilbert. If you are interested in any of this and really enjoy it, self-plug, Gilbert and Stephen are actually going to be running a course next semester. As long as you've taken 230, you will satisfy the prereq, CS 390R. So yeah, with that, Gilbert, take it away.
All right. Hey guys, so this workshop today is kind of going to be a bit of a continuation from last workshop. So we're going to briefly brush up on some of the topics from there and then continue on to binary exploitation related topics. Just for the content of today's workshop, we're going to start with a brief introduction about what is binary exploitation, then move on to some of the basics that are required, such as assembly, so basic systems knowledge. Then we're going to discuss some common vulnerability classes, quickly introduce two tools we're going to be using, one of them being GDB, the GNU debugger, the other one being Pwn tools, which is a Python library that will make our lives a bit easier. Then we'll be introducing a simple exploitation technique, and in the end, I'll have some challenges for you.
You can also take your mask off if you want.
That's okay. All right, so first, what is binary exploitation? So it generally starts off with finding a vulnerability. There are three main methods of doing that. First one is static analysis, dynamic analysis, and then there's a few other ones such as fuzzing or symbolic analysis. Static analysis, basically what you did in last week's or the workshop 2 weeks ago with Jacob. You opened up a binary and disassembler. You looked at the code, reverse engineered it. That's static analysis. Dynamic analysis is generally when you actually run the program. So you can either, in terms of malware, something you just run the malware, see what it does. That's basic dynamic analysis. Generally, you're going to want to put the software in a debugger, step through it, see exactly what it does. Then there's fuzzing. That's basically when you generate semi-random input, send it to a program, and hope something crashes it. For example, you take an image parser, send it images, and randomly corrupt bytes in the image and hope one of the one of the corrupted images eventually crashes the image parser. If you're interested in that, I'm going to be hosting another workshop on fuzzing during Hack UMass, so check that out in that case. Okay, then after you find the vulnerability, you need to look to exploiting the vulnerability. At that point, your goal is generally to either gain control of the program, spawn a shell, or just leak sensitive data sometimes even. Some common vulnerability classes that you may have heard of are buffer overflows, format string vulnerabilities, integer over and underflows, heap metadata corruption, which can occur with heap overflows, double freeze, use after freeze, and several heap bugs, and race conditions. Those are like the common ones. You can find in pretty much any architecture, any system. And there are more target-specific vulnerabilities, such as in browsers. You have type confusion bugs and some other stuff.
The arrow keeps me.
Okay, so we're going to start with the basics. That was already covered last workshop. The last week's workshop, so we're just going to cover that quickly. Registers, they're a memory location within the processor. It's kind of similar to RAM, but much smaller and much faster. This is the set of main registers that you're going to be seeing on X86 64. They're 64 bits wide, and they can hold any value. It can be addresses, characters, arithmetic operands, whatever. It's basically just bytes. They can be accessed by some of their smaller subsections, as you can see. RAX, for example, it's a 64-bit register, but it has smaller subsections. EAX, which is its lower 32 bits. AX, which is the lower 16 bits. And AL, which is the lowest 8 bits, and that's how it works for all of the registers, pretty much. We have a few special registers that are not general purpose. Those are usually used for specific purposes. First, the RIP register, that's the program counter. This keeps track of where you currently are in the program while executing it. It holds the address of the currently executing instruction. So RIP is always, if you look at RIP, that's the next instruction you're going to be executing. Then there's RSP. That holds the stack pointer. So the stack is just another region of memory. We'll be discussing that in a second. And RSP is basically used to designate where the stack ends. And there's RBP. This is technically still a general purpose register. You can use it for other purposes than what it's usually used for. But generally, compilers use it to as the entry to a stack frame buffer. So in a function, every function sets up its own stack frame, and the RBP register is used as an address from which local variables can be referenced from as an offset. We're going to be discussing the stack a bit more in a second, so that will hopefully make sense. That's okay. Okay, so the stack, it's an area of memory. It's generally used with the RSP register. It's a stack data structure. You can push values onto it, you can pop values off of it, and the RSP register just designates where the stack is currently located. So stacks are used to store function arguments. You can store local variables are stored on the stack. So if you write a program in C and declare a variable int x equals 5, this 5 is stored on the stack. And it's stored to, and it's used to store function frames. So whenever you call a new function, a new frame on the stack is basically created that the function uses for its local variables. When the function returns, the stack frame is no longer valid, and is basically just free memory again. So here comes the first important point towards exploitation. When a function is called, the function's return address is stored on the stack. So when you call a function, for example, in main, you call the function add. Then you go into add, do whatever add does, and then add needs to return to main so you can continue operation in main. So you need to store the address in main. You need to store that somewhere. So that's stored on the stack. So there are a lot of vulnerability classes such as buffer overflows that aim to overwrite values on the stack. So when the function actually tries to return, instead of returning to where it's supposed to, it can return to the value that you overwrote it with your vulnerability or with your exploit. We're going to go more into that in a bit. Quickly, the X86 Calling Convention. When you call a function, you oftentimes want to provide arguments. This is the one that's used by X86. The first argument is held in the RDI register, the second one the RSI, and so on. And if you have more than 6 arguments, the remaining ones are stored on the stack in reverse order. Okay, we're going to go into 8 assembly instructions. Most of those were covered last week already, but first one, push. It increases the stack size, or on x86 64, it increases stack size by 8, and the value stored in racks is placed on the stack. So you can push registers, or you can also just push immediate values, such as the push 4, which is basically the exact same, just you reference an immediate value instead of a register. And there's the pop instruction. This basically reverses the push. It decrements the stack size by 8 and stores the value in the register that it was called with. There's the add and subtract instructions. They operate pretty much exactly the same. You can subtract 2 registers, register and intermediate, and basically just addition. The result is stored in the first register in Intel assembly syntax, such as you can see there. Okay, next few instructions. The move instruction, it's used to copy values from one location to another. First one in this example, it copies the value 5 into the racks register. The second one, it copies the value that's currently in RBX into the racks register. The third one, it has the bracket notation, which in Intel assembly syntax means that instead of storing RBX into RAX, it stores the value that RBX points to into AX. So in this case, RBX would be an address, and that address points to a value somewhere else in memory, and that value is stored into RAX instead. And the last instruction is basically the same as the last one, just that that address plus an offset of 4 is stored into racks instead. The next instruction is the call instruction. It basically pushes the return address onto the stack, and then it jumps to the function. We haven't discussed jump, but it's basically just, it sets the RIP register, the one that sets where your program counter is currently located. It sets it to the function address. So you store the return address, and then you go to the function. That's what call does. An example is below call printf. It just calls printf pretty much. The leave instruction, leave and ret are a set of instructions that are generally used at the end of functions. The leave instruction basically stores RBP into RSP, and then pops RBP. This basically, so these instructions basically just retrieve the stored function pointer from the stack, or the return address that was at. So when the function was called, the return address from the previous function from the callee was stored on the stack, and this function epilogue basically retrieves that address, and then the return instruction pops that value off the stack and jumps to that address, basically returning from a function call. Okay.
Asking people a question.
Yeah, does anyone have a question in that regard? I went over that a bit quickly, but if you have questions, completely fine. I can elaborate on some points. If not, we're going to see some examples in a bit that hopefully showcase it a bit better. Yes?
Why do we move RSP from RBP? Why do we store RBP into RSP?
So RBP is that's the frame pointer. So that's at the beginning of the stack of the function's frame, and the return address is located at the beginning of the frame.
Okay.
So by moving RBP into RSP, the RSP value now points to the beginning of the frame. So when you then pop a value off the stack, it pops it off the beginning of the frame. Since the pop instruction basically always interacts with RSP and just takes the instruction that's at RSP, or the bytes that are at RSP. So that's basically done to like retrieve the return address, if that makes sense. Any other questions? Okay. So here's a small example program. The main function declares 3 local variables, 2 of which are initialized to 1 and 2. The third one is left empty. And the local 3 variable is initialized to the return value of the add function with local 1 and local 2. And so add is called with 1 and 2, returns the value of 1 plus 2. So local 3 is assigned to 3, and then printf prints out local 3. Does that make sense to anyone, or to everyone, I assume? Okay, it's basically just like a very simple function. Now let's look at the assembly of that. So here's the main function, and at the top you see the add function. So are the 2 functions we just saw in our program. Actually, there are like a lot more functions in theory that the compiler adds in, but these are the 2 we just saw in the source code. These are the 2 we care about right now. The rest are kind of relevant for us as of right now. So looking at the main function first. The first 2 instructions here, push RBP and move RBP RSP, are basically the function part of the function prologue. They're done at the start of every single function, and just serve to set up the function frame. Next, you see a sub RSP 0x10. This decreases the stack by 16 bytes. So this is actually done to make space on the stack for the local variables. Now, it's decreasing it because it might sound a bit weird, but I believe it was touched on last workshop. The stack grows downwards. So by decreasing the RSP pointer by 16 bytes in this case, you just made 16 bytes on the stack that you can use for local variables or whatever else you want. So this basically sets up the stack. You now have 16 variables to work with. Now, during the function call, or never mind, not yet. So here you see the local variables. The first local 1 and local 2 are initialized here. You see RBP points to the beginning of this function's stack frame, and at a negative offset from RBP, we store the value 0x1. Another negative offset from RBP, we store the value 0x2. So that basically stores 2 4-byte integers onto the stack, and uses the allocated space by the sub instruction, and uses the RBP register as like a reference point for these instructions. So 1 and 2 are now stored on the stack, which is how local variables are initialized in this case. Next, you see the RBP minus 0x8 value is stored into EDX, and the other value is stored into EAX. So this pretty much, so these variables are both stored in the stack first, and now they're moved into registers. Why is this done? Working with memory is slow. Working with memory does not allow you to do very much, or it does limits the amount of instructions you can use, because a lot of instructions are forced to work on registers and not memory directly. So here you see the call to the add instruction, and if you remember earlier, we discussed the calling convention. Quickly look at it again. So the first argument is an RDI, and the second an RSI. Add has 2 operands, x and y, so that should equate to RDI and RSI. And if you look at this here, value 1 and 2 are stored in these 2 registers respectively, and then the add function is called using the call instruction. So at this point, execution is then transferred over to the add function. This, once again, has the function prologue of setting up the stack frame. Next, it moves the 2 parameters that were passed to it into local registers, so EDI and ESI, or into local memory. So EDI and ESI are both moved into the functions stack frame. Next, these are once again passed into registers. The registers are added together, and the function returns. So this might look very inefficient because we move from registers to memory and then from memory to other registers, and it is very inefficient, but we're compiled without optimizations. And that's just how the GCC decided to handle it in this case. Another thing to notice, when a function returns, the return value is always stored in the RAX register. So in this case, you see the add instruction adds EAX and EDX, which contains its two parameters, and stores the resultant EAX. So at the end, during the function prolog, which actually in this case is a pop RBP and red instead of a leave and red, which not exactly sure why right now, but it's probably because it didn't have to change the stack size with a sub-instruction, so it could leave out. But yeah, so it stores the result into EAX and returns. And at this point, the return address, which is this address right here, the 118A, so this address was stored on the stack when the function was called. And at this point, when it returns, this address is retrieved. It's put back into the RIP register, the one that holds the instruction currently being executed. And the program jumps to this location, which is after the add. Okay, if you remember what happened next. So the add function was called, and local 3 is assigned to the result of the add function. So let's see how that is handled here. We see that as I mentioned earlier, the result from the function is stored in the EAX register. So the function return, this return value is EAX. So that is now moved into RBP minus 0x4, which is the value that it's the address on the stack that's allocated for the local 3 variable. Then that value is once again moved into a register. This register is moved into another register. And then here's something a bit confusing or interesting, what we're going to call it. So printf, so it wants to use the RDI register as an argument to printf. So it takes an offset of RIP and moves that value to. I'm not going to discuss it too much right now, but it basically just sets the RDI register to the local 3 actually. Okay. So we call printf with a string that includes the format string, the %s. And this part needs to be saved somewhere. So the RDI is the first argument. The first argument to printf is the string you can see here. Local 3 is %d new line. So that's the first argument to printf. The second argument is local 3. So here you can see with this instruction, it takes a value out of memory, which is in this case from the data section that contains the string, and it's saved to RDI. The ESI register is already set here with the value of local 3, which was retrieved here. So here printf is called with 2 arguments, the first one being the string, the second one being local 3. So it executes the printf instruction, returns, or the printf instruction we don't have open right now, it's very long and very complicated, we don't have to look at that. After printf completes, returns back here. EAX is set to 0, and the floop is handled again, thus returning 0 from main and quitting the program. So that was hope not too confusing as your one of your first introductions to assembly. Yeah, does anyone have questions? This was probably a bit confusing. No one? Yeah.
Yeah, I'm just a little confused about the purpose of the pop command at the end of the add function. So I see that the EDX is added with EAX, and then I think I remember that RBP is the return value, but when is the value of that addition moved into RBP? Or is that...
So in this case, it restores RBP back to the previous function's frame. So when this function called the add function, this function's frame pointer was stored on this function stack. So the pop RBP basically restores this function stack frame into the RBP register, so that after the call completes, you can once again reference RBP minus 0x4 to reference this function's local variables instead of the upper function's local variables. So basically, RBP before the pop RBP points to the add function stack frame. After the pop RBP is then set to this function stack frame once again, then it returns, and then this function can once again use RBP to reference its local registers instead of the add function's local registers. that make sense?
Yeah, I think so.
Okay. Anyone else? Yes?
So in the add function, why does it transfer the value of EDI, ESI into EDX,
Into EDX and EAX. So the add instruction, it cannot operate on two memory locations. So it first needs to store the memory, so the value into register, and then it can add the two registers together. So with the move from memory into EDX and EAX, it basically retrieves the values from memory into two registers, and then it can perform the add instruction onto the two registers. If you're wondering why the other two moves are up there, so technically, if this entire function could have been simplified a lot, could have just stored the values into EDI, and it could have just taken ESI and EDI, added them together, moved the result into EAX, and returned. The function would have still been worked out just fine. You wouldn't have needed all the memory accesses, would have been a lot faster. But we compiled without optimization, so GCC just has it exactly how we laid it out in the C code. Nothing was really changed. So this is what we get, which is very unoptimized, but it displays kind of what we asked for. But yes, this could be a lot. A lot of instructions in this sequence could be saved if we compile with optimizations. Okay. Any other questions? Okay, let's move on then. So let's get into cybersecurity a bit. Here's a small set of code, 40 lines approximately, 4 vulnerabilities in this code. Anyone want to see if you can find them? Yes. Read data. How do you? Mm-hmm.
Will only exit if it's 76. So you can go over 64 and overflow.
Sorry, can you repeat it?
Well, since the max block is set to 64, and if you're checking the length to be
Okay. Anyone else? So yeah, there is a buffer overflow, but it's a bit more complicated than that. But maybe anyone else want to give it a go for vulnerabilities in this code? Okay, we haven't really discussed vulnerabilities yet, so okay, so let's discuss them real quick. First one, line 19, is a call to gets. Gets is initially just a completely unsafe function. You should never use it. It basically just takes as much input from the user as the user wants. The buffer variable is initialized to 64 bytes, so gets into buffer. The user can write thousands of bytes into that buffer if he wanted to, and that would completely overflow the stack, corrupting all the data. If you remember, the variables are still stored on the stack, so the stack made room for maybe like 20 bytes on the stack. In this case, would be more, maybe like, let's say around 100 bytes maybe for the buffer of 64 bytes and some other stuff. It allocates 100 bytes. And then the user gives it 200 bytes. What's going to happen? It's going to start corrupting other stuff on the stack. The stack has return addresses, it has pointers, it has a lot of stuff that it does not want corrupted. But with this buffer overflow, you can corrupt everything pretty much. Okay, next one, printf. This immediately prints out a user-controlled buffer without any format strings. Do you know how printf format strings work? So printf has like format strings like %p, %x, %d, which actually in the previous example here, you saw me use the %d, which basically references a value stored on the stack, or in a register in this case. Or actually, yeah, and uses it for %d. So what this here allows you to do, in this buffer, you can fill it with format string specifiers. So you can put in a %s, %ps, and thus the %ps are going to try to then, printf is going to interpret that as a format string specifier. And then the %p, for example, if you put in like %p here, that is going to try reading a data off the stack, which there is no data here. There are no arguments to this printf call. So it's just going to start leaking out random variables from the stack, which is an address leak, which like results in data leakage, and you don't want that at all. Third vulnerability, have an infinite loop here. scans a number into choice, and then takes 3 different paths depending on what you choose. Case 1 allocates a pointer. Case 2, it frees the pointer. So from like the previous heap vulnerabilities I mentioned, can you think of something you might be able to do with this? Okay, so one of the heap vulnerabilities I mentioned was a double free. So if you choose the first case, it allocates the pointer. And then let's say you choose case 2 twice in a row. You're going to free the same pointer twice. First iteration, the pointer is freed. The second one, the pointer the memory is not in a state where it wants to be freed anymore. If you free it again, it's going to lead to memory corruptions, which can be exploitable in certain situations. This last bug is up in the read data function. There is a buffer overflow in here, but it's a bit more complicated. So if length plus 12 is bigger than max buffer, it exits. So you need to provide an input that's smaller than that. How are you going to do that? Well, if you look a bit further up, length is an integer. Integers can be positive or negative, and if integers reach their max size, they're going to overflow and become negative. So in this case, if you provided a max size integer, it's going to overflow and then become a negative value, thus passing the max buff check, and then the fgets function is going to interpret that number as a positive number again, and you'll have a massive million bytes overflow. Okay, we're going to discuss, I kind of just like went over them very quickly. Yes?
Can I add something?
Yes.
So there's one more issue which is related actually to all of those, which is the fact that you don't check the return value of scanf. So given that you don't do that, you actually don't know whether you ever read that integer. And that means that you might simply have an uninitialized variable with whatever happens to be on the stack, and that itself might get you a big integer value of the kind of way.
Yes, that is very true too. Yeah, so we're going to discuss the vulnerability class a bit more in a second. But yeah, 40 lines of C, a lot of vulnerabilities might look obvious here after you heard of them, but once you get into bigger programs, have thousands of lines of code, much more complex, these vulnerabilities get very hard to spot sometimes. So let's talk about the stack buffer overflow. It's probably the most common vulnerability. It's been around since 1960s, 1970s. It's very long. So we discussed it a little bit, but the point is basically you overflow a local buffer that's stored on the stack. This could be pointer stored on the stack. This could be variables that shouldn't be changed, but you can change using an overflow. This could even be the return address, so you can completely change the flow of the program. Generally, the goal is to overflow the return address and thus hijack program execution. That's generally the easiest method, what we're going to be going for today as well in the challenges later. You overflow local buffer, you overwrite the return address that's stored at the stack, and when the function tries to return, it returns to the value you provided instead. So you can basically completely control where the program goes. You can inject your own code, for example, and then have the program jump to your code and execute that instead of what it's supposed to do. And that's a very serious vulnerability. There are various exploitation strategies. The two that are very popular. First one was return to shellcode. This basically you inject assembly instructions that execute basically execute a shell. So you know how you have your bash shell in the Linux terminal? You're trying to execute that program. So you inject shellcode that basically sets up the appropriate registers and calls execv with this value. Now, this was the first popular exploit strategy. Then it became very popular. It became very bad. And we needed something to fix it. So mitigations were introduced, and new exploitation strategies had to be developed. There's return-oriented programming, for example. It's another technique to exploit stack buffer overflows. It may be a bit, we're not going to discuss that yet. Maybe in a bit. So for the mitigations, there are many more, but these are 3 very popular ones. First, there's NX. This makes it so memory regions are either writable or executable, never both. So with return to shellcode, your goal is generally, within your buffer, you inject shellcode onto the stack, and then you take control of the RIP register and jump to your shellcode and thus execute the shellcode. This now makes it so the stack is no longer executable. So if you try to put your shellcode on the stack and jump to it, the program's just going to crash. You can't execute your own code anymore. So that was one of the first major mitigations that were introduced, and that's how return-oriented programming was born. Very high-level overview. Instead of jumping to your own code, you jump to instructions that are already in the binary, in the text section. So you can no longer inject your own code and jump to it because it's, so you can no longer jump to like your own code that you injected, and instead you need to find something else. So you jump to instructions that are already in the program. So in this example, for example, if you wanted to set the RBP register, you could jump here, which would execute a pop RBP and then return to the next address on the stack. And you basically create a chain of a bunch of these little sets of instructions that are already in the binary, so they're executable but not writable. So you can't change them, but you can still jump to them and execute them. So execute a bunch of instructions that are already in the code and kind of just jump through and execute the code you want to inject that way. It's too complex to properly explain today, but it is a very popular technique. Next, another mitigation is ASLR. It randomizes addresses. So you know how I've been saying that you generally want to like jump to an address where you either have your code or for your ROP chain. Well, this just got a lot harder. The addresses are now randomized, so you can't like just look at where this address is that you want to jump to and just go there. You now need to leak an address, and then it's not every address is randomized. So binary program memory has different segments, and these segments are their base addresses randomized. So the program code is stored in the text section, for example, and then the base address, so the start of the text section, that address is randomized. So if you leak out a single address from the text section, you can then use that address to calculate all other offsets in this section. So your goal to bypass ASLR is usually you leak out a single address from the section you're trying to use, and then you can suddenly know all the addresses in that section. Another mitigation is stack canary. It's a magic value that's stored at the end of a function on the stack. So if you're going to try to overflow buffer, you're going to pass the stack canary and overwrite the stack canary before you overwrite the return address. And then before the function exits, though, before it like actually returns to your instruction, it's going to check if the canary is still intact first. So if you overwrote the canary, then the program's just going to see, oh, there's something wrong occurred here, and the program's going to exit. This canary is also randomized, so you can't just predict what the canary is and overwrite it with the value and move on. The canary is going to be randomized. You don't know it. If you overflow, the program's going to crash, so that is pretty big against buffer overflows. And the general approach against it is also similar to ASLR. You leak out the value, and then you can put it into your payload. Here's a very simple example of a buffer overflow. You allocate a small buffer on the stack. You read in 50 bytes into the 28-byte buffer, thus overflow memory. Okay, does anyone have questions on the buffer overflow? Or anything we just covered so far?
This kind of goes back to what you were talking about before. So we were talking about like printf, right? And it's not safe. So I was wondering, is there any way, like, what are the alternatives to that? Because I know, like, at least in a lot of classes we use printf. Would I like write to like standard out?
Okay. So printf on its own is safe. You just can't. Actually, let me go. I'll talk about it in the next slide. Actually.
Okay.
All right. Anything else? Okay, let's move on to format string vulnerabilities then. These are the ones that interact with printf. So the vulnerability occurs when a user-controlled argument is passed to a printf-like function. That could be printf, could be sprintf. There are like multiple variations. And it occurs when it's passed to a printf-like function without format specifiers. So the argument itself can have format string specifiers. So in this case, the buffer variable, so printf only extracts format specifiers from its first argument. So if you put the buffer, the user-controlled buffer as the first argument, it's going to extract format string specifiers out of this buffer. However, if you make it a string and then, for example, put a %s format, so if you make the first argument of printf a string with the %s format string specifier and set the buffer as a second argument, it's no longer vulnerable because it's going to take the %f and just the %s format string specifier and just take the value from buffer. it no longer interprets the buffer itself as basically potentially format string specifier. So what can you use this vulnerability for? So it's very commonly used to leak values off of the stack. So as I just mentioned, ASLR and Canary, both of them randomize addresses, store random values on the stack, and you need those values for your exploit. So printf vulnerability, for example, you can inject %ps, which basically leak out addresses from the stack. And then if you leak out a correct offset, for example, if you put in 3%ps, it's going to leak out 3 values from the stack. And then you can potentially leak out a value that you can use to calculate ASLR addresses or even the Canary. That's one way to, one thing you can do with it, and actually something that's going to be in one of the challenges as well. Another thing you can do with a printf vulnerability is are you aware of the %n format specifier? So all the other printf format string specifiers, they just take a value of the stack and basically put it into the string in some form, %d as a number, %s as a string, and so on. The %n format string specifier, however, it works a bit differently. Instead of storing a value from the stack into the string, it takes the string and stores it, or it takes the amount of the length of the string prior to the %n and stores it into the first argument. So this you can actually use to write to addresses. So you can not just leak memory with a format string specifier, you can actually overwrite basically arbitrary points in memory, which, similar to buffer overflow, you can then, if used smart, you can use to hijack control or control of the program. I'm not going to cover how to do that today because it gets fairly complex, but that's something you can do. Does anyone have questions about that they want to ask? Okay. Let's move on to integer over and underflows. So on the right, you can see a small table. It has various types that are used in C and their value ranges. An integer, for example, a 4-byte integer, which is generally used on most systems, can have approximately the size of -2 billion to 2 billion. If you overstep that boundary, what's going to happen? So let's say you have this number and an integer, and then you add 1 to it. Well, the variable just cannot store. It only has 4 bytes. This is the maximum value that can be represented by 4 bytes. So what's going to happen? It's going to roll around, and suddenly you have this large negative value. And that can lead to very bad unexpected behavior, which, so in this little example program, 2 integers are, so the main function, 2 integers are declared. The first one is set to the maximum integer value here. The second value is set to this value plus 1. When you then try to print out both integers, the first one is what you'd expect. The second one is suddenly, instead of being just 2 billion and whatever and 8, it's -2 billion and 8. So that can, like, similar with like the example I mentioned earlier, that can like lead to some pretty bad logic bugs. And even like if this value is potentially like passed to fgets, could also like lead to buffer overflows and so on. Does anyone have questions on that?
As I said before, is there ever like what's the practical reason for having a %n? Like, is there any use case you could think of that isn't exploited?
The %n format string specifier.
Yeah. Seems like not very useful.
I have personally never used it in one of my programs, but you can't. Do you want to say something about that?
Yeah, Google says that you can like, if you're writing multiple lines of output, you can get the previous lines or the count of the previous lines, so you can like format things to be all line.
Oh, okay.
And
yeah,
that's one use case.
Okay. Since the %n value stores the amount of bytes that were written prior to it into the variable, that can then be, you can then use that to like basically extract how long the previous string was before the %n, which I guess can be useful in certain cases.
Which also relates to the fact that printf returns the number of characters printed.
Yes.
But you have a very good point, which is that in general, if you're designing something, you want to design something that is as simple as possible. Like when you're introducing complexity into something which is really supposed to be used in a simple way by many people, yeah, you run into exactly what you pointed out.
Does Does anyone have any other questions? Okay. Another bug class is heap metadata corruption. We're only going to be touching on that very shortly because even attempting to explain the exploits would go way over the scope of this. But when you dynamically allocate data on the heap using, for example, malloc, the memory allocator basically takes a region of memory and gives you a pointer to it. And then you can use that region of memory of your requested size to store data in it. Now, it doesn't just give you a region of memory. It also needs to have some way of this needs to be fast. So it needs certain metadata to create linked lists of 3 pointers. So for example, if you request 3 bytes of 10 blocks, or 3 blocks of 10 bytes, you're gonna have 3 pointers. Let's say you free the first one. Then instead of just discarding the memory, the heap allocator is something a bit smarter. It puts the memory into a free list. So if you request 10 bytes again, it's going to just look at the free list and then can give you your previous 10 bytes back, and it's a lot less overhead. Now, why is this bad, or why can this be bad? So all this metadata is stored on the heap right next to your data. So if you have an overflow in your program, you can suddenly corrupt heap metadata. So you can, for example, corrupt the size field of the next chunk. You can corrupt pointers on the heap. You can do all sorts of things that can lead to big messes on the heap and corrupt basically everything. So, yeah. There are some common bugs: use after freeze, double freeze, heap overflows. Use after freeze, basically if you free a pointer and then allow it to be used again afterwards, this can create issues. For example, let's say you make an allocation, free it, then this variable should no longer should be used for that section. And then you make a new allocation. This new allocation, as I mentioned with the free list, is going to use the same memory region as the. Actually, it's just not. This is not, no.
Take our class.
Yes, we're going to be going into that a lot more in detail in there. Just to put it into perspective, though, a 1 byte heap overflow can already be enough for a full system compromise in certain situations. So 1 byte overflow can corrupt the size field, which you can then potentially use to corrupt much more on the heap and lead to very serious exploits. So just a single byte can already be enough in certain situations, which led to 2 common, or maybe not common, but 2 exploitation strategies for heaps that can operate on a single byte overflow, and it can be very dangerous. Okay, now we're gonna, enough theory for now, we're gonna talk about tooling. First one is GDB. It's the GNU debugger. It's pre-installed on every Linux system pretty much. Are all of you aware what a debugger is? Or is anyone not aware? Basically just lets you set breakpoints in a program. You can break on specific instructions and view the memory at that state, for example, see what's going on. Programmers use it to debug their programs and whatnot. We'll be using it for our exploits. So some GDB, so we'll go into an example in a second. Here are some instructions that are important. First, to start GDB, you open the command line and use GDB against the binary. There's the start command. It starts running the binary, and it sets a breakpoint at main, and then it starts running the binary. So it basically runs and then breaks as soon as the program hits main. Then to the NS or the N instruction, the S instruction, NI and SI instructions. So the N and S instructions are pretty much just used if you're using GDB with source code available. You can use that to basically advance 1 line of C code. It's generally a lot less relevant to binary exploitation because you don't usually have that source code available to you. The other ones, they don't go, so this goes a line of C code. This goes 1 assembly instruction. The NI and SI instruction are generally what we're going to be using. The difference between NI and SI is, NI, if you, for example, have a call printf and type in NI, it's just going to instantly execute printf and go to the next instruction. If you type SI, it's instead going to go into the printf call, and you can debug printf itself, for example, if you wanted to. This is how you set a breakpoint. You can specify B for break. You can also type out break if you want. Use a dereference symbol and type in the address that you want to set a breakpoint on. This can also just be a function name in our case. So you can write B, the star main, and it's going to set a breakpoint at main. Or similar for the add example, you can set B star add. If you run the program, it's going to break at add, and you can view the register, the memory, everything. The P instruction stands for print. You can use it to print out a register or memory region or whatever you want. The X instruction stands for analyze, I believe, or examine. You can examine. You can use it to syntax is a bit confusing here. You can basically also use it to look at variables on the stack. Memory operates a bit different than print. In this example, for example, you type x/4 stands for 4 instances that you want to print out. X stands for hexadecimal, and W stands for words, which are 4 bytes in this case. So this would print out 4 hexadecimal words, so 16 instructions at the RSP address. Bit confusing, but we'll go into an example in a second, or actually, no. Okay. Yeah, I think so. If you want to follow along with this, so we're just gonna be looking at the add program again. It's actually posted in the Discord. You can there's a zip file in the general, you can download it. It's basically just the add function from earlier, so you can also just type that down if you want to and follow along. All right. So here you once again see the source code of the function of the program from earlier. There's the main function. There's the main function. It has its relocable registers, calls add, and so on. So now let's look at that in GDB. So we're going to open the program with GDB. In this case, it's called add. So I'm just going to type GDB add. It's going to run the program. Well, that's unusable. Okay, this should be usable. Okay, so as we saw earlier, let's start with the general start instruction. That's going to put us at the beginning of main. So this was actually so this program was actually compiled with debug symbols, so we can actually see the source code. So if we're now at the beginning of main, as you can see here, we're on line 7 of the source code. At line 7 of the source code, begin at int main. So in this case, we could just type n to go over cin, basically a C code instruction, and we are now at the first declaration, and so on. Now we're at the second. Okay. That's very basic usage. So there's I didn't mention this command before, but there's the disassemble command. You can use that to basically view the instructions of a function. So if we, for example, use disassemble main, we suddenly get all the assembly instructions of the main function. This will remind you of, actually, I just changed the syntax to Intel assembly because AT&T is weird and we haven't covered that. But this is the main function and GDB view. So you can see all the instructions again. As you can see, there's this little arrow. That's the address we're currently located at. And we're at the one of the move instructions for the local variables. So now we can, for example, use the NI instruction and move on an instruction. So if we just went down 2 instructions. If we disassemble again, we now see that we're at this instruction instead. Okay, so if we look at the previous instruction which just executed, one of the local variable, which contained 2, was just stored into the EDX register. So if we now use the print command to look at EDX, we see that EDX has been set to 2 by using print EDX. We can continue another instruction. This instruction just this instruction just set EAX to 1. So if we now type print EAX, you're going to get out 1. So now we're going to disassemble again. Going to move on 2 instructions. So now we're on the call. So we are calling the add function now. you remember what I said, the arguments, and which register arguments are going to be stored? Anyone remember that? Or can infer from the source code? Or from the assembly? What registers hold the 2 arguments to the add function? Okay, maybe we went a bit too fast. But so in this case, you can see EAX register is stored EDI, EDX register and ESI. These 2 registers hold the 2 arguments for the add function. As discussed earlier, the RSI and RDI, the ESI and EDI are like the 32-bit smaller parts of these 2 registers. These hold the arguments. So if we now execute the SI instruction, this moves us into the add call. So if we disassemble again, we can now see the add function. We're now in the add function at the first address of the add function. So we can execute 2 NI instructions, actually 3, jump past all the setup or the function prologue. We're now at this instruction. So the next instruction is going to move the EDI register, the first argument, into a local variable. So we can do that. And now the RBP, which is the frame pointer, minus 0x4 or minus 4, should have the first argument to the function. We can confirm that by, once again, printing RBP minus 4. Again, so print in this case, as you see here, did not actually print out the value that we expected. Why is that? Print just takes the value at face pretty much. So in this case, RBP minus 0x4 is a memory location. So as you can see here, it printed out a very large number. This is a memory location. This is actually where the value is stored. So if we instead go back to one of the other earlier instructions, the examine instruction, we use x/d for decimal, and then access RBP minus 0x4. We're going to get the address, and what it points to is 1, which is the first argument to the function, as expected. Move on another instruction. As you can see, this next instruction moves the ESI register, which is the second argument, into RBP minus 0x8. So if we now instead look at RBP minus 0x8 instead, it has the value 2. So as we expect, our variables made it into the local frame of the add function. Now they're going to be once again stored into the EDX and EAX registers. Now if we look at it now, we're at the add instruction. So next instruction is going to add the EAX register to the EDX register. Let's look at what EAX is. 2. EDX, 1 or 2. What we expected. We execute the add instruction. If we look at EAX now, it's 3. So the 2 registers added together, results are in EAX. If we disassemble again, 2 more instructions to go. We're going to restore RBP. And now we're at the ret instruction. So this is something interesting again. So ret basically moves the value at the top of the stack into the RIP register and thus transfers execution. So if we examine the address at the top of the stack using this command, RSP for the stack pointer, X for hexadecimal, and G for quad word, which is going to be 8 bytes. We get, so this then prints, so this is the stack address, and this is the address that's located at the stack address. And so as we see, it's 0x5555188. So if we disassemble main and look at that address, it's this one. So compare those two, 0x5555188. That's the instruction right after the call to add. So this ret instruction here, once executed, it's going to move this value into RIP. Then RIP suddenly points to this instruction instead, and we resume execution in main. Let's try that out. So we execute the ret instruction. And if we now look at what's at, let's say, the next 5 instructions at RIP, we see we're back at main, where we expect it to be. Okay, move on a little bit. 3 more instructions, and now we're at the call to printf. Larger. We're now calling printf. It's actually saying printf.lt, which I'm not going to explain now, but just don't worry about it. So we're calling printf here. If we look at printf's arguments, so x/s we're going to examine as a string, and RDI, which is the first argument. First argument, local 3 is %d/n. Seems to be as expected. I just typed in the wrong register. And then if we print out the second argument to printf being RSI, we see the value 3. So this executes what we expected. Local 3 is %d with the second argument as 3. So we execute printf, and we see it's printed out here. Local 3 is 3 as expected. In this disassembly, we're now at the move instruction. It moves 0 into AX, and then it basically returns from main. So, and the process exited normally, returning 0. So we just use GDB to basically walk through the entire program step by step for each instruction, so seeing exactly how memory was laid out. This is a skill that maybe in software dev you're not going to be using much. This is assembly-based debugging. Usually you're going to deal with source code in that case. In binary exploitation, you're going to be dealing with a lot of assembly when debugging and trying to figure out how to exploit your software. This is a skill that's very important to build up if that's something you want to do. But this was a simple example now, how we can go through a program. I promise GDB syntax becomes a lot less confusing once you get used to it. Does anyone have questions on this? Okay.
Second. What do you say? It's better first.
I think we can stay here because it's only like one slide and then we'll go. I need to pretty much include them. Let's look at the slides again for a second. Okay, so we just discussed GDB, a couple of commands we just used. I'm going to have a cheat sheet up for you later once you actually work on the challenges, so you can refer back to the commands. You don't have to memorize them immediately. After you use GDB for a while, you will memorize them automatically if you do decide to go that way. Here is this pawn tools. I'm not going to talk much about it today. Short summary, it's a Python library. You're going to be, in binary exploitation, once you do more complicated exploits, you want to script them out. So while you can just input 50 A's into the program manually, once you need to make hundreds of different inputs to the program, you're going to want to have some script to do it for you. You use pawn tools for that. It's a Python library. This is the setup. You basically specify the program you're trying to use it on and import the library into your Python script. It has a lot of useful commands. We're not going to need most of them today. Only ones we really need, apart from the prologue, is p.sendLine and p.interactive. The p.interactive one, it basically keeps session open with the program, so you can send your input and then it's going to keep session open. So if you send your input and this input spawns a shell, the p.interactive command is going to keep the standard in open so you can actually use the shell. You can do it manually with shell commands, it just makes it more comfortable. Very similar to p.sendLine. This just basically sends what you specified to it, so you can specify a string here, and that string is sent to the program. One last thing, you don't really need it, but it's helpful. Addresses are stored in little endian, as mentioned last workshop, so they're stored in reverse order. This basically reverses the bytes and appends them to the size. So 64-bit is 8 bytes. So it's going to reverse this address basically and append 0 bytes until it's padded to 8 bytes and can be used as an address. You could type this out manually. This just makes your life a little bit easier. Okay. Let's get to the first actual exploit we'll be writing, or yeah, probably the only one as well during this talk at least. It's very simple. We have a main function, allocates local buffer, size 40. It asks a question, what do you want to say, and then gets our input. As discussed earlier, gets is not safe at all. You can give it as much as you want, but it only has 40 bytes. So that's an issue. So what if you go 200 bytes and you're suddenly going to overflow the return address? That's not good. Another thing you can see in the program here is the win function. It basically says, congrats, you hacked your first program, and X includes a shell for you. So normal programming knowledge should tell you in this program, there's no way win should be called. There's no call to win, it's just exists there. But your goal will be, in this case, to call the win function anyways. Up here is the Gcc Compile Command. You don't have to worry much about the flags. This disables the stack canary, and this disables ASLR pretty much for the win function's address, so you don't have to worry about leaking a value or the stack canary. You can just do your exploit and override the value. And we're going to be exploiting that together now. So just going to pull up the source code here. Oh, yeah, that's okay. Is this weird too with the touchpad?
Do like control plus or minus here.
Okay, this should do the trick. Okay, so up here, top left, you see the program that we just looked at. Okay, so program is called ret to win. Let's run it. Ask us, what do you want to say? You can say, hello, exit as expected, nothing special happens. What happens if we instead give it a bunch of A's? Now, program can hold 40 bytes on buffer. We just gave it a few hundred A's. Segmentation fault. So the main function, at the end, it tried to return. Instead, the return address was overwritten with a bunch of A's, probably. And it can't return to the address of 8 A's. That's not a valid address, so it segmentation faulted. Now, this alone doesn't tell us that much, so let's open it in GDB. And let's run start. Okay, we're at main. So we can look at the function again. Function prolog. It makes room on the stack for 0x30 bytes. That's more than we requested, but 60 more bytes actually. But that's fine. Compiler does stuff, needs more stuff. It just, yeah. Then it sets up the puts call by saving the address into RDI. Actually, let me change this again. GDB defaults to AT&T syntax, which is, I don't like it. So back at main, this time a bit more readable. Subtracts from RSP, then sets RDI, which is the first argument to puts, to, if we look at this address, we can run examine/s to look at a string and specify this value. And, actually, it referenced RIP, and RIP is not there yet, so we can't, so the string is kind of cut off until RIP is actually at this, but yeah, okay. So let's start stepping through the program, make a couple of steps, see where we are right now. Oops. Okay, we're at the leave instruction, so if we execute this instruction again, this time we see the actual that's not good. I'm confused. Okay, we're at the puts call. Okay, so now it appears to work again. Oh, because I tried reading the memory before it was moved into it, so I just printed out something unexpected, which my fault. So now the instruction executed. If we try looking at the RDI register again, you can see it contains the string that we're trying to print. What do you want to say? We execute puts. String is printed. Okay, let's press. We can type in continue and move on. Just continues the program, so we're not single stepping through everything. Let's provide it a bunch of A's again. Okay, GDB, we receive a segmentation fault, and we're back at the break prompt from GDB. this point, we can use the info registers command. This prints out all the registers. Most of these we don't really care about, but if you look at the RBP register, it's set to 0x4141414141. This is basically the character A in hexadecimal. So you can see here that we overwrote the RBP register with 0x4141. We don't really care much about that right now, but it's interesting. We definitely act something out of bounds. This is not supposed to happen. Now, if we look at RIP, it's not actually corrupted here yet. But if we look at the instruction that we sec faulted on, it's a return instruction. So it wasn't able to successfully complete the return instruction. So the return instruction takes the topmost value from the stack. So let's look at the stack. Stack's located at RSP. Let's print out 4 words at RSP. And as you can see, these 4 words are all A's. And so the actually let's do this. This is probably more readable. So we use quad words because 64-bit addresses are 8 bytes long. So this address at the top of the stack. This is what it attempted to move into return. This is not what return wants. So return wants to set RIP to a valid location in memory, but this is not mapped. It's not valid at all. So the program sec faults, as you mentioned saw earlier. So anyone want to take a wager on how we could potentially use this to call the win function somehow? Anyone want to give it a go? Yes. Yes, good. So that's going to be exactly our approach. We'll find the address of the win function, and we'll overflow the buffer and set this address here. Instead of 8 A's, we're going to set it to the address of the win function. In GDB, we can get the address. We just do print win, and here we see the address of the win function. 0x401176. You can also, if you're just out of curiosity, print out the address of main. It's at 4011A3. We're not going to be needing it, but just to see it, print out address with the print function. Okay, so let's get working on our Python script. Refer back to the slides. Little cheat sheet. So here's the these two should be swapped. This is GDB. This is Clone Tools. But okay, first line. Okay, we import the Clone Tools library. Then we set the elf. Yeah, I was just copy paste this, so even after thousands of times of doing this, I still don't remember the exact syntax. Okay, so we have our setup complete. This basically sets up a interaction with the program. So set the PR interactive at the end. Okay, now our commands to interact with GDB, the main one that we're going to be using right now is the p.send line. So we can use p.send line. And let's just send it a hello message. Just doesn't overflow, shouldn't do anything malicious. Okay, let's. This is fine. Okay, let's just execute this real quick. Because it's not actually called vuln, it's called read to win. So, okay, let's try this again. Interacts with the program. What do you want to say? Sends the command. Nothing else happens in the program, but see, was probably successful. Okay, let's try doing something it's not supposed to do. Let's create a payload variable and set it to. Let's give it 200 days. Okay, I just can't type on this. Okay, let's give it the payload equal to 200 days. And then instead of sending it hello, we send it the payload. Let's see what happens now. Actually, you can't really see much more right now it's sec fault. Let's actually look at that in GDB instead of this first. Let's run the program again. And this time, instead of just giving it something normal, actually, we already did that. Okay, let's look at the main function. Figure out how much we want to overflow. So we see the stack allocates 0x30 bytes. And so we can start with our So we need padding to get to the return address. So we have 0x30 bytes to cross first. So we can add that to the payload. So that can be anything. We just add 0x30 bytes of A's. So this is almost going to be enough to get us to the return address. The RBP register, or the return address from main, where the stack frame is actually pushed onto the stack as well. So that's another 8 bytes. So we can specify this. And let's just do this. And actually, we're just going to do this manually first for a second. So we're just going to have Python give us all those bytes and run the program again. And this time, give it this input. If we now look at it's sec plotted again, we look at RSP. It's 0x424242 instead of the 41. So we gave it 8 A's and a bunch of A's and 8 B's. And we managed to get the B's over the return address. So now, if we want to exploit that, we just need to replace the B's with the address of win. So let's get the address of win real quick. So we can do it either with pwn tools, which makes it very simple, like this. Or we can also, if we wanted to do it manually, which would be basically just like construct it and fill it up with bytes. Yeah. Okay, what? This doesn't even fit on the line here, whatever. So we can use this, which basically it's going to fill up the buffer with 0x38 A's. And then this next address, which is the P64 of the win function address, is going to get stored over the return address. So let's run our exploit, see what happens. Yes, we got the congrats message. So we successfully redirected. This message is in the win function. There's no reference to it in main. We overwrote the return address with the address of win function, hit execution here, printed out the congrats message, and then executed a shell. We can now with a shell, we can execute commands here, and that's basically how, if you lived 50 years ago, you could exploit systems, or probably even like yes. Nowadays, there are a lot of mitigations. It gets harder. There are a lot more techniques to learn. You need stronger bugs than just this. For example, if ASLR was enabled, you could no longer do that. You would need an address leak, not just a buffer overflow. You also generally don't have a win function, so there's that too. So you would have to like create a rob chain. There might also be a stack canary, so another value to leak. So there's just a lot more to deal with nowadays. But if you are interested in getting started with exploit development, you can start at 0 and move up. And yes, does anyone have questions about this? Or have issues following along, reproducing it, or anything they want to ask about it? Okay, and finally, CS390R, Reverse Engineering and Vulnerability Analysis. This is a new course introduced to the UMass CS major for next semester. It's going to be taught by Steven and I. The prerequisite is CS230, and it counts as a 300 level CS elective. We'll be covering topics such as stack exploitation, including all major mitigations. We're going to talk about how to bypass them. We're going to talk about format string exploits, integer issues. Going to even go into heap exploits, learn how exactly the heap works, the glibc heap, learn how to corrupt the metadata, and in the end, if we have time, even do some kernel exploitation. If you're interested in like learning how like the Linux kernel memory works, for example, we're going to go into that a little bit as well. So if you're interested in taking that, it's going to have 30 available spots. You can register for it on Spire once registration opens. And that is basically going to be what we did today, plus a lot more. And that's it for the workshop part of this. I have 3 challenges prepared. They are all in the zip file that's in the Discord, in the challenges directory. They should be doable with what we learned today. So if you want to give them a go, look at them. You can ask me questions. You can send me a message on Discord. I'm Gilbert, and I'll be happy to help you. You can try them now. And yeah, that's pretty much it if you don't have any questions.